I was debating about how to cover the remainder of your week 1 course material in soft chalk, so I'm going to, due to limitations of video size, hopefully I'll split this up into multiple segments. But consider this part 1 of your monitor unit calculation introduction. So let's start off and write the monitor unit equation across the top, and then we're going to go through all of the factors. Okay, across the top we have dose and centigrade. S sub C and S sub P are your output factors, so these combined make S sub Cp, which is your total output factor. So as far as the units go, this is in centigrade per MU. So if you have centigrade per MU, the centigrades drop out, the monitor units go to the top, and that's how we get MU. So the monitor units work out. Everything else is a relative factor. Okay, they're unitless. All right. You have to remember that these radiation machines are calibrated by the physicists, and they're calibrated under very specific reference conditions. We've mentioned this before, and John Smith had it in his PDF very eloquently about physicists making sure that the rest of the dosimetry staff in the department know exactly the exact reference conditions that the machines are calibrated. Let's take a reference condition. In our case, let's say 6X is calibrated to deliver 1 centigrade per 1 MU for a 10 by 10 field size at 100 centimeter SSD. Okay, under those exact conditions, if I dial up 1 monitor unit in the machine, I deliver 1 centigrade at Dmax. Okay. Now, once we start deviating from this, then we start doing monitor unit calculations and dosimetry. Okay, and you will never treat in the clinic this ever. 99.9% of the calculations you will do will never be like this, especially for photons. So let's start talking about these. S sub C and S sub P. S sub C is the collimator scatter factor. This accounts for the change in collimator size, change in dose rate with collimator size. We talked about dose rate, field size dependence. This is kind of a corollary to that. There's a difference between S sub C and S sub P. Okay? S sub C is the collimator scatter factor. It has to do with two things. First is I increase my collimator aperture area, I have more physical area along the edges for the radiation to scatter off of. Note my area here in the smaller aperture, and note the increased area in the larger aperture. So the total surface area increases, therefore the total amount of scatter increases because of that increased surface area. The second part that adds to the collimator scatter factor is the scatter that comes from the flattening filter in the head. So at really small field sizes, we start blocking the flattening filter and we start really decreasing the output caused by scatter from that flattening filter. If I had to draw a picture for collimator scatter factor, if we wanted to measure it, I would put a detector in the center of a volume that allowed charge particle equilibrium, so we're basically at Dmax, and I have a beam coming down. And there's no other phantom material around here. The idea is that all dose detected at that ion chamber, that detector, is purely from scatter from the collimator and scatter from the head of the machine. There's no phantom scatter. There's no scattered radiation out here that's going to be scattered in and detected at the detector. Okay? In fact, physicists do this. They do this for a variety of field sizes and whatever energies they have in the machine. Next is the phantom scatter factor, S sub P. What does this account for? This accounts for the increased dose rate due to the increase in scatter within the patient. Well, we call it the phantom in the patient. Okay? So to illustrate this, if I have a phantom surface or a patient surface, and I have my point of measurement here, I have one field size, I have a larger field size. I now have additional scattering material out here with the larger field size that I didn't with the smaller field size. So now I have not only direct dose contribution from the primary beam here, but any interactions out laterally can be scattered in that weren't able to be scattered in from the smaller field size. Now, you make an argument and say, well, yeah, but you're also changing the collimator size, so you're increasing the collimator scatter factor. You're right. That's why S sub p cannot be measured. Okay? It's impossible to measure. I shouldn't say impossible. People don't measure it. What people do is they measure S sub c using this method, and S of Cp, which is the total scatter factor. This measurement geometry is technically the total scatter factor measurement geometry because I'm measuring both phantom scatter and collimator scatter. So if I have S sub c times S sub p equals S sub Cp, okay, I cannot measure this, so I need to figure it out. So how do we figure it out? Well, doing a little math, I measure the total scatter factor in phantom, and I divide out the collimator scatter factor, and that gives me my phantom scatter factor. Okay. Again, collimator scatter factor deals with scatter from the collimator head and assembly. Phantom scatter factor deals strictly with scatter within the phantom. Okay. And S sub Cp is the total scatter factor. S sub Cp is in centigrade per monitor unit, or the units. Okay, so that's how our dose rate changes from 1 centigrade per mu for 10 by 10 field size. We modify it with the total scatter factor. Things that go smaller than 10 by 10, I should say that everything's normalized to a 10 by 10 field size. So 10 by 10, S sub Cp equals 1. For less than 10 by 10, S sub Cp is less than 1 because I have less dose. If I'm at greater than 10 by 10 field size, S sub Cp is greater than 1.0. I encourage you at your facilities, machines are different between Siemens, Varian, and Electra, the three main manufacturers. The machines are slightly different in their output factors because A, they have different collimator head assemblies, and B, Varian has a tertiary MLC, the other two use an MLC as a jaw. So the scatter factors are going to be just a touch different. So I would encourage you to pull out your physics data book wherever you're at and look through these scatter factors and see how much do they change. How much do they change going from a 3 by 3 to a 10 by 10 all the way up to 40 by 40, which is the maximum field size that most of the machines are capable of delivering. Okay? What is this? This is 1.0. And what is this? What's the range? What's the range for S sub c? What's the range for S sub p? What's the range for S sub Cp? How much does it change? Consider this part 2 of the monitor unit equation video. In the previous video we described S sub c, S sub p, and S sub Cp, the collimator, phantom, and total scatter factor, and how it changes the dose rate on your machine when you dial up monitor units. Next I want to talk about wedge factors. I know that TMR was next, but I want to talk about if we put something in front of the beam, okay, whether that's a tray or a wedge, what happens. So remember our monitor unit equation. Tray factor, isodose line, inverse square law, and off-axis factor. Some people call it off-axis ratio. So these two are done. S sub c, S sub p, the total scatter factor, S sub Cp, TMR we'll go back to. Now I want to talk about wedge factor and tray factor. First of all, tray factor is the easy one. So all a tray factor is it's an attenuation correction factor. We don't really use trays anymore because of the advent of MLCs. We don't use Sarabin blocks. Occasionally, maybe once or twice a year, or depending on your department, you may have to cut a photon block. In fact, as a dosimetrist, I would encourage you, if they still have a block cutting machine, that you try and cut a few photon blocks and have the other physicists or dosimetrists help you out with that, because that would be a nice skill to have to bring to your resume. So if we have a Linac beam, this is a phantom surface, patient surface, and we have a point of measurement, and if I deliver 100 monitor units, I get a specified amount of dose here. For the sake of simplicity, let's just call it 100 centigrade of dose. Okay? Now, if I stick something in front of that beam, a tray, I stick a tray on there because the blocks, the photon blocks, sit on top of the tray, right below the aperture of the collimator assembly. So this tray is made of acrylic. It has some sort of attenuation for it. How does the physicist measure it? He takes a measurement without the tray, and he takes a measurement with the tray. He takes with the tray divided by without the tray, and that gives an attenuation factor. This attenuation factor for 6x photons is normally right around 0.97, 3%. By sticking this little acrylic tray in there, I attenuate that beam 3%. I need to adjust for that. If I deliver 100 monitor units without the tray and deliver 100 centigrade, if I deliver 100 monitor units now with the tray in here, I deliver 97 centigrade. I don't want 97 centigrade. I want 100 centigrade. So what do I have to do? I have to adjust my monitor units that I dial up on the machine. So I take 100 divided by 0.97. That gives me my new monitor units that I dial up. Again, it's an attenuation factor. That's what we're doing when we put the tray factor in here, is we're adjusting the monitor units higher to account for a decrease in output because of the attenuation by the tray. Now, wedges are a similar case. How do we measure a wedge factor? The physicist measures without the wedge and with the wedge, and he divides the two. So the wedge factor is strictly a transmission factor. Okay? It's nothing else. What are your wedges made out of? I encourage you, go on your machines at your clinic sites and go in the room, pick up the wedges, handle them. What's the thickness of the wedges? How much do they weigh? Are they bulky? Are they difficult to put in the machine? How do you put them in the machine? What are the wedges made out of? I mean, what materials are they made out of? Okay? All it is, the wedge factor is a transmission factor and nothing more. Okay? And just like the tray factor, we have to account for the transmission or the attenuation of the beam in that wedge. Okay, so to measure the wedge factor, we'd have the reading with the wedge divided by the reading without the wedge. And that gives us our wedge factor. But the wedge factor will always be less than 1. Always. It has to. Okay? Now, as a dosimetrist, if you forget to put the wedge factor in your monitor unit, you will potentially overdose the patient by a lot, or underdose the patient. I should say, if the dosimetrist forgets to put the wedge factor in the patient, we will underdose the patient. If the therapist forgets to put the wedge in the machine, you will overdose the patient. Okay? Well, how does that work? If I have radiation beam coming down, patient surface, this is my point of measurement. Again, to keep the numbers simple, I dial up 100 MU to deliver 100 centigrade. Okay, as a dosimetrist, okay, we put a wedge in this machine. It's made out of metal, and it attenuates the beam. Let's say the wedge factor is 0.5. It attenuates the beam by 50%. Okay, if as a dosimetrist, if you forget to put the wedge factor in the calculation, what's going to happen is you're going to tell the therapist to dial up 100 monitor units. How much are they going to deliver? They're not going to deliver 100 centigrade. Half the beam's been attenuated. They're going to deliver 50 centigrade. Patient's going to be underdosed by half. Huge. Okay. As a dosimetrist doing your second hand calc, you should be plus or minus 5% for normal geometries. You know, the goal for some facilities is less than 2%. You know, the goal of the hand calc is to catch gross errors. Okay, if you forget to do the wedge factor, this is not a gross. This is a misadministration. Patient receives less than half the dose that they wanted to. Okay, so what do? We need to put the wedge factor in the beam. So if I put a wedge in the beam, and I want to deliver 100 centigrade, how many monitor units do I dial up if my wedge factor is at 0.0 or 0.5 at 50%? Well, I need to dial up twice as many MU, so I need to deliver 200 MU. Now, from the therapist's standpoint, most modern linear accelerators, they have multiple interlocks that will prevent you from doing this, but you never know. Things have been known to go wrong. So what happens is that from the therapist standpoint, if you plan it with the wedge, and if they forget to put the wedge in, now they're delivering 200 centigrade with no wedge, they're going to deliver 200 centigrade to the patient instead of 100 centigrade, and they're going to overdose the patient by twice as much. Okay? This is why documentation, communication, and safety checks by the physicists are so important. Consider this part 3 of the monitor unit equation breakdown. This one I want to concentrate. This goes in with a wedge factor and an off-axis factor, and it involves talking about beam profile. The physicists, when they do not their calibration, but their modeling of the beam, okay, they sit down for a weekend or 40 hours or so, and they scan the beam. They scan depth doses, vertically along the beam, and then they also scan in-plane and cross-plane profiles. Cross-plane profiles would be left to right, looking at the gantry. In-plane would be in and out in the couch direction. Okay, and they put all this along with the field-dependent dose rates into the treatment planning computer, and then it allows the planning computer to model the radiation beams in virtual reality. So we need to talk about beam profiles. If I have a radiation beam, this is my treatment head up here, radiation beam coming down. If I scan across the beam from left to right, that's what I'm talking about when we mean beam profiles. Okay. Now if I were to graphically represent this, how would this look? How would this look? What we have is I'm going to draw for a 10 by 10 field size. And we have some specific parts of this profile. We have here, we call these the tails. There's always going to be some radiation present. There's leakage from the treatment head, and then there's also scatter radiation from inside the beam that's always going to give us these little asymptotes that go out. All right. We get a curvature up. Notice that it's not a straight line. It doesn't go straight up, straight over, straight down. The beam does not look like that. Okay, we're limited to the laws of physics. We curve up. I come up over a shoulder, dip down in the center, come back up to a shoulder, and I get the same thing on the other side if our beam is symmetric and flat. Okay. Now, the different parts to this are I have 100% is on the central axis. Everything's normalized to the central axis. Okay, and these are the different parts of my beam profile. I have what's called the full width half max, which is going to be my 50% isodose line. Okay, my 50% level. That corresponds to the light field. The light field in the treatment machine dictates the 50% isodose line. I have 20% is another magic number, and 80% is another magic number. Now, the region going from 20 to 80% is called the penumbra. Most manufacturers are going to specify the penumbra as the 20% to 80% line. In Khan, you'll read it that it's either 20 to 80 or 90 to 10, but most people use 20 to 80 because it's a smaller width than 90 to 10, and it makes your machine seem like it has a tighter beam. So when you talk about the tightness of the beam, okay, the tightness of the beam is how small is the penumbra, because the penumbra represents the fuzziness of the beam, the fuzzy edge of the beam. If your physicists do monthly QA, and if they still use film for a radiation light field check, I would encourage you to look at the film. The film will not show just a black square there will be a slight fuzziness to the edge, and if you put it on the white box, you will be able to see that. And the fuzziness that you're seeing is this penumbra. Again, 50% isodose line represents the light field or field size definition. These up here we call horns, and they vary in size depending on the energy that you use and the depth that you're at. And the horns are caused by the flattening filter of the beam. We can hopefully discuss that at a later time, why that's the case. But they will be there at shallow depths, and they will not be there at deeper depths. Okay? Most machines are designed to have their flatness and symmetry specified at a depth. You know, whether that's Dmax or 10, most of the time it's 10, since most treatments are, I shouldn't say most treatments are 10 centimeter depth, but most treatments are at depth rather than Dmax, so they make it flat at 10 centimeters. The flatness of the beam is going to be defined by your maximum point divided by the minimum point. That's your flatness. The symmetry of the beam is if I pick a point here and an exact point on the opposite side from the central axis, and I divide those two, that's my symmetry of the beam. The beams need to have a specified flatness and symmetry. You can ask your physicist to talk to you more about that. What happens when I put a beam modifying device in the field? What happens if I put a wedge in the field? How does that affect my beam profile? So now, if I draw a beam profile, I'm running out of room, and I put a wedge like this in the field, what does my beam profile look like? Remember, everything's normalized to 100% on the central axis. So I still get my penumbra, I still get my tails. Under the toe of the wedge, I get increased radiation because I get less attenuation, thinner part of the wedge. I get 100% at the central axis, okay? And then I get less radiation under the heel of the wedge. I still have penumbra, I still have tails, everything's normalized at 100%, but now I am over 100% under the toe, and I am below 100% on the heel. How much those percentages are depend on the type of wedge that we put in. This is going to be greater for a higher wedge angle, meaning like a 60-degree wedge, but it would be less than if we used a 15-degree wedge. The same case happens for enhanced dynamic wedges or virtual wedges. If we use a 15-degree wedge, roughly, as we go in part 3 of the MU calculation, we talked about the beam profile. We described an open field profile and the wedge profile, and how the toe and heel of the wedge affects that beam profile. This ties directly into the off-axis ratio part of the monitor unit calculation equation. So if the physician or you happen to want to calculate the dose to a point that's not on the central axis, we need to apply an off-axis factor, or called an off-axis ratio. And all this is it's a ratio of the dose to a point off of the central axis. We'll call this point A, and we're going to take it to a ratio that to the dose on the central axis. So if I had off-axis factor for point A, it's going to be dose at A divided by dose at the CAX, the central axis. And that's all it is. Note that this is going to be greater than 1 for an open beam, because everything is normalized to 1.0 on the central axis. So off-axis factor equals 1.0 on the central axis. For an open field, it's going to be roughly plus or minus 3%, the entire length of the field. Not the case in the wedge field. So the wedge field that we drew earlier, if this is the wedge orientation across the beam and we scan left to right, this is the profile that we create. Now there are some general rules of thumb that we can use to describe how much that off-axis factor is going to be. For a 15-degree wedge, for every centimeter that you go off axis, you're going to increase or decrease roughly 1 to 2%. For a 30-degree wedge, 2 to 3% per centimeter. 45-degree wedge, 3 to 4% per centimeter. 60-degree wedge, 4 to 5% per centimeter. Remember, this depends on the wedge and the machine that you have, but these are just general guidelines to go by. So if I move 1 centimeter toward the toe with the 60-degree wedge, I'm going to be 5% hotter than I would on the central axis. If I move 2 centimeters towards the toe, because of the greater attenuation, I'm going to be 2 times 5, 10% hotter. So how does the off-axis factor work with this? If I have point A, and point A is 1 centimeter from the central axis, and if I follow this general rule, my off-axis factor is going to be my dose at point A, call it 105, divided by dose at the central axis, so 1.05. Again, with the monitor unit equation, everything is relative. Everything works in fractions. So it's a dose in centigrade divided by a bunch of fractions, or percentages. This is my off-axis factor. If I go off-axis the other way, towards the heel, let's say to point B, my off-axis factor for point B is going to be 5% less, is 95, divided by the dose on the central axis, which is 100, and I'm going to get 0.95. Okay, so I'm 5% cooler off-axis toward the heel, and 5% hotter toward the toe. Off-axis factor, again, accounts for the change in the intensity of the beam as we move off the central axis of the beam. Okay, it's particularly important for wedged fields. We want to talk about the depth modifying factor in our MU calc equation. We've gone through collimator scatter, phantom scatter, which together are the total scatter factor. We've done wedge factor, both the transmission and the off-axis component. Tray factor is a transmission factor. We have yet to do inverse square law and isodose line, or normalization. But now we're going to talk about TMR, or percent depth dose, PDD, or TAR, tissue air ratio. Any of those are going to be a depth modifying factor. Remember, the machines are calibrated for a specific energy at a depth, for a field size, an SSD, to deliver a specified dose per MU. So for 6X at 1.5 centimeter depth, 10 by 10 field size, 100 centimeter SSD, we calibrate the machines to deliver 1 centigrade per monitor unit. So let's get on with percent depth dose, or TMR. So let's talk about percent depth dose first. Remember percent depth dose? The definition: I have a 100 centimeter SSD setup. I have a Dmax point, and then I have some other reference point down here that we'll just call point A. Recall that percent depth dose is dose at Dmax divided by, dose at A divided by the dose at Dmax. Okay, and this gives us a ratio. So it's the percentage at depth relative to Dmax for a 100 centimeter SSD. Now, let's draw this out. This is going to look very similar to the build-up discussion that we had the other day. Let's take 6X right now. Okay, so I have 100% dose. This is my skin surface at 0 centimeters. Characteristics of the beam are at 1.5 centimeters is Dmax, so we have around a 30% to 40% surface dose for 6X. We get a buildup to a maximum dose at 1.5 centimeters. It peaks and then it begins to taper and fall off in the patient. Again, build up, because we have photons interacting, the secondary electrons get scattered. They scatter to a maximum and deposit their dose at 1.5, and then we get an attenuation of the beam, so we get fall off. Draw the 50% in here. My percent depth dose at 10 centimeter deep is going to be 67%. Again, this is for 6x, or 6MV. Okay. What happens if I change the energy? Well, I guess what's percent depth dose dependent on? Percent depth dose? It's going to be dependent on depth. As you can see, as we change the depth, I get a change in percent depth dose. It's going to change with the energy. If I have an 18 MV beam, now my surface dose is right around, we'll call it 15%, 15 to 20%. My max dose is going to be 3.5 centimeters. My depth dose at 10 centimeter deep is going to be 78%. So how does percent depth dose change with energy? It increases. How does percent depth dose change with depth? As we increase the depth, percent depth dose decreases. As we increase the energy at a relative depth, percent depth dose increases. So as percent depth dose goes deeper, percent depth dose goes down. As we go higher energy, percent depth dose goes up. What happens if I change the field size? Now, instead of a 10 by 10 field size, I have a larger field size, and we'll call it 20 by 20. So I've increased the field size from 10 by 10 to 20 by 20. Well, what happens to my percent depth dose? Well, what happens to the dose at point A? What happens at the dose at point A? If I had 100 monitor units delivered through here, and I figured out my percent depth dose for 10 by 10 field size, and it's 67%. Okay, I'm at 67% of the dose compared to D max. If I deliver that same 100 monitor units, am I going to get a larger dose or a smaller dose at point A? I'm going to get a larger dose. Why? Because of the scatter from outside here that we didn't have before. So now I have photons. We talked about this with the field size dose rate dependence. I have photons that come in and they interact out here where they couldn't before, and they can get scattered to A and give an increased reading at that point. So I will have a higher reading at A with a 20 by 20 than I did at 10 by 10. Well, what does that mean? Look at the equation for percent depth dose. If I increase the dose at point A, this dose stays the same, my percent depth dose goes up. So as I increase the field size, my percent depth dose increases. Graphically, what that looks like, let's take 6x. Everything looks similar to D max, except my percent depth dose is a touch higher because I have a higher reading at point A. So the last thing is SSD. What happens if I change my SSD? If I change my SSD, my percent depth dose increases. And I'll explain this in another lecture because it's a little bit longer explanation. So what's percent depth dose dependent on? As percent depth dose, as depth increases, PDD goes down. As energy increases, PDD increases. As field size increases, PDD increases. As SSD increases, PDD goes up. Okay, so that's percent depth dose and what it's dependent on. This is a follow-up to the percent depth dose discussion, and this is my attempt to describe how percent depth dose varies with SSD and why it depends on SSD, and why we need the Maynard F factor when we calculate monitor units based on a percent depth dose setup. The dependence on SSD has to do with the inverse square law. Let me draw a couple diagrams. If I have, we'll call this my source, and I am 1 unit back from my source. Okay, that's my starting position. If I take 1 unit move back using the inverse square law, I have decreased my intensity by doubling my distance, right? I'm 1 away, I then am 2 away, I've doubled my distance. Remember, inverse square law, intensity is proportional to 1 over the distance squared. If I double my distance, I get 25% or 1/4 of my initial intensity, right? 1 unit away, I move to 2 units away, 1 over 2 squared, 1 over the distance squared, 25% or 1/4 the original intensity, okay? Now, same source. This time, I'm starting 2 units away. I'm starting 2 units away. But I only move 1 more unit away. Okay? I've taken the same motion backward as I have here. I move 1 unit. Here I moved 1 unit away from the source, but my starting position has already been 2 units away from the source, further from the source. So how does my intensity drop off then? Well, I1 over I2, D2 over D1 squared, okay? Intensity 1, intensity 2, D2 over D1, D2 is 3, D1 is 2, is 9 over 4. My ratio, if I flip this, I2 to I1, is 4 over 9. And what is 4 over 9? 0.44 or 44%. Okay? Case 1, I took 1 unit move away from the source. I'm 25% lower. I'm to 25% of the original intensity. Case 2, I move 1 unit away, but I started further away. I move 1 unit away, and this is I'm down to 44% of the original intensity. Okay, notice the difference between these two. This is the exact situation as an extended SSD setup. Watch. Source, patient, phantom, whatever. I'm at 100 centimeter SSD. My calculation depth is at 10 centimeter deep. That's where point A is at. That's like this. Point A. Now, case number 2, source, point A is still at 10 centimeters deep in the water phantom, except now I'm at 130 centimeter SSD. I've moved further from I've started further from the source. That's this position here. I've moved the same amount, 10 centimeters, 10 centimeters. I've moved 1 unit here, 1 unit here. Okay? Is my percent depth dose going to be greater or less than in this case? It's going to be greater. I'm going to have a greater percent depth dose than this case because I'm at a further starting position from the source, which was just illustrated up here. 1 unit back, 1 unit back. I get completely different intensities based on the inverse square law. This is why percent depth dose depends on SSD. And this is why we need to correct for it with the Maynard F factor. Okay, the last two on our list are going to be isodose line or normalization value and then our inverse square law correction. We've talked about the collimator scatter factor, the phantom scatter factor, the fact that the combination of the two are the total scatter factor, a depth modifying factor, whether that's TMR or PDD, transmission factors of wedge factor or the tray factor. And we've talked about the off-axis ratio or off-axis factor and how that changes whether you have an open beam or a wedge beam. Next is going to be isodose line. Some people put norm here for normalization. Even though we're never going to give a straight 6x beam in the clinic, just for illustration, let's do this where we have a patient surface and we have a field, and let's just say we have our tumor target is here. And let's say we deliver, to keep the math simple, 100 monitor units, and the isodose lines look like this. Where we'll call this the 100% isodose line, and this is going to be the 95%, and this will be the 95%. Now you might ask, well, how do we get 95% on both sides? Well, if you remember the percent depth dose curve, this was 100%. Well, I have 95% here, and I have 95% here, because we have 95% in the build-up, and then 95% in the build-down as well. So I have 95% on either arm. Well, you deliver 100 MU through the beam, and my 100% goes straight through the middle of the target. Well, we don't want that. We want the 100% isodose line to cover the target. So what can we do? Well, I can say, well, we can just calculate to a deeper point, right? True, we can. That in effect will be normalizing to a deeper, a different percent depth dose. Is the same thing as prescribing to a different isodose line. All this is it's normalizing. That's why these are all fractions, they're ratios. They're just normalizations based on where the point is at in space. So in this case, if we want to keep isocenter here, and we don't want to calculate to a different point, I can prescribe to a different isodose line. In this case, I can prescribe to the 95% isodose line. So I can say, okay, instead of the 100% being my prescription dose, I want to make the 95% my prescription dose. So I'm going to bump everything up 5% higher. So this is going to be 105. These are going to turn to 100. You might ask, well, how do we do that? Well, we just pump more MU in. So instead of 100 MU, I'm going to give 105 MU, roughly. So I'm just pumping more energy in to give me more dose. So instead of 100, I'm giving 105. Now my 95's turned to 100, 100 turns to 105, 95 turns to 100, and now my 100% prescription line looks like this. And I have treated the tumor to my dose that I want. The next thing is going to be the inverse square law. So let's see, we've done this, we've done that, we've done this, we've done this, we've done this, we've done that, we've done this. Last one is inverse square law. So inverse square law is going to be source to calibration point divided by source to calculation point squared. So if your machine is calibrated, let's take a simple example of 6X. If it's calibrated at 100 centimeter SSD for a 10 by 10 field size, 1.5 cm depth, okay, to deliver 1 centigray per MU. All right. Now, we don't treat SSD technique in the clinic anymore. For 99.999% of the patients, they're SAD technique, source to axis distance. Okay, and we use a TMR or a TAR to calculate. And we do that because we want an isocentric technique. The gantries are mounted isocentrically, so they rotate 360 degrees around the patient. We don't want to have the gantry at a 0 angle and flip the patient upside down to do a PA field. We're way beyond that. So, but our calibration is calibrated at SSD. So how do we correct for that? Well, in this case, if I want to, we'll call this example 1. You know, if I want to calc to isocenter, okay, my inverse square law correction is going to be source to calibration point, which is 100 centimeters plus 1.5 for the depth is 101.5. My source to calculation point is isocenter, which is located at 100 centimeters SAD. It's at the axis distance, this squared. So you get 1.03. So my inverse square law factor is 1.03. Well, what that means is I take the dose, if I have a number divided by a larger number, I get a smaller number. So my monitor units need to be adjusted lower to account for the inverse square law. Well, why do they need to be adjusted lower? Why do we need to adjust for it? Remember, let me draw the geometries. This is my source. This is the calibration geometry. I'm at 100 SSD, I'm at 1.5 centimeter. This is where I'm calculating 1 centigrade per monitor unit. Now look at my treatment geometry. Call this calc point. Look at my treatment geometry. In my treatment geometry, I'm closer by 1.5 centimeters. I'm closer to the source than 1.5 centimeters. This is where 1 centigrade equals 1 monitor unit. Okay, remember from the inverse square law lectures and examples that I've now moved 1.5 centimeters closer to the source. Okay, that's why we need to correct for it. So I get hotter, the radiation gets more intense the closer to the source I move. Therefore, we need to decrease the monitor units necessary to deliver the dose to that point by 3%, 1.03. Okay. What is the inverse square law for 15x, 18x, and 10x? I encourage you at your facilities to look this up and go ahead and calculate that. Another example would be that if our calc point isn't at the isocenter, but it's somewhere else, let's say it's 5 centimeters away from our 100 centimeter SAD. Okay. Now how do we calculate the inverse square law? Okay. Inverse square law is going to be the same thing as 1.015. That's our source to calibration distance. Source to calibration distance is going to depend on the facility that you're at as well as the energy that you're calculating. And now my source to calculation point is going to be 100 because I'm 100 centimeters SAD to the isocenter, and then I'm an additional 5 centimeters. So I'm 105 centimeters, and this whole thing is squared. Okay, this number is going to be less than 1. Notice that I'm beyond my 1.5 centimeter. This is where 1 centigrade equals 1 monitor unit. I'm past that. The radiation is getting less intense as I move past this point. Okay, I'm accounting for that by dividing my dose by a smaller number than 1. Therefore, I increase the number of monitor units that are needed. Make sense? Electrons are used in radiation therapy for superficial treatments. There are two components to this. Number one is electrons have a high skin dose compared to photons, as well as the electrons have a physical range within tissue, so at some point the electrons stop depositing their dose completely, as opposed to photons, which will keep going through the patient indefinitely. So if I have two patient surfaces here, one with a photon field and one with an electron field, my photon field will continue to have isodose lines at depth, whereas the electron field will stop. their only dose component at depth for the electron field is something called photon contamination or Bremsstrahl contamination. So electron treatments are primarily used for superficial treatments, usually skin tumors, a lot of times breast boosts for boosting the lumpectomy cavity. Dosimetric characteristics of the electron field. So if I draw a percent depth dose curve for let's say 6E, so 6 MeV electrons, my surface dose is right around 75%. I get a fast buildup. My Dmax is right around 1.5, similar to 6 MV or 6X. And then I get a very fast fall off. Contrast this, so I'm just going to call this 6E, which is the same thing as 6 MeV electrons. Contrast this to 6X, where I get a surface dose between 30 and 40%. I get a build-up region. It peaks at Dmax, and then I get a fall off. So contrast these at depth, the doses. Parts to the electron curve. Things with the electron curve you need to know about are going to be surface dose. Okay. How does surface dose change with energy? For photons, surface dose decreases with increasing energy. For electrons, surface dose increases with increasing energy. You need to know about something called D90, D80, Dmax, R50, and R sub P. Okay, so D90 is going to be the depth at 90% isodose line, which roughly, you take the energy divided by 4. Okay, that gives you a good approximation. D80 is going to be the depth of the 80% isodose line. Again, roughly is E divided by 3. Kahn specifies these more accurately. Your physicist should also have these written in a data book somewhere. Dmax in general increases with increasing electron energy, but we find out, when you actually look at percent depth dose curves with the electrons, that the higher energies don't really exhibit one particular Dmax value, but rather a plateau. R50 is going to be depth of the 50% isodose line, and this is normally an energy qualifier, so it's how the physicist specifies the effective energy of the electron beam. R sub P is going to be the practical, we'll call the practical range of the electrons, and the definition for this, or the approximation for this, is energy divided by 2. Okay, so I would encourage you to build the following table out and verify it at your clinical sites as well. So we'll have electron energy, and 6, 9, 12, 15, and 18. Electron energies depend on manufacturer as well as what the site orders up. Usually, sites will have some range in here. They might have like a 20 or a 22E. Maybe you have a 16 instead of a 15. It's up to you to verify your own electron energies on your machine. What I want you to do is build the following table. Is build surface dose, D90, D80, Dmax, and R sub P for each of these, and convert it to memory for your particular site. I always stress dosimetrists at your clinical sites or at your job that you will eventually get. You need to kind of commit these to memory, or a general rule of thumb. You need to remember them. Okay. So how does percent depth dose, let me go back. Percent depth dose. Let's draw it a little bit bigger. And let's compare two different energies. Okay, we'll compare 6E sorry if the scales aren't going to be drawn out correctly. So this is going to be 6E, and then we'll compare that with 20E. And I'm only picking these two because drastically different. So points to make about the two percent depth dose curves and how the percent depth dose curves are changed by changing the electron energy. First thing, skin dose. Skin dose goes up with increasing energy. They roughly work in, let's see, 5% increments. So 75% at 6E, 80% at 9E, 85% at 12E, 90% at 15 or 16E, and then 95% at your 18, 20, or 22E. Okay, but again, those are just rules of thumb. You need to go back and verify that with your data book. Next thing is going to be D80 and D90. I guess here we have D max for 6E. And notice that for 20E, there's no specific D max. You get this broad plateau, of 100%. So D max is usually can either be specified, in the middle, or sometimes the physicists will write a range. It'll go from 1.5 to 2.5. Okay. Next is D90. So D90, and then you'll have D80. You have R50. Right, and then you have R sub P. R sub P is found by taking the tangent to your fall-off line. If you track it and extrapolate it down to the axis, this is where R sub P is at. On the 6E, I would track the tangent down to the axis, and R sub P would be here. R sub P for 6E is going to be 6 divided by 2. Energy divided by 2 is going to be roughly 3 centimeters. R sub P for 20E is going to be 20 divided by 2, or 10 centimeters. R sub P represents the practical range, or the physical range of the electrons travel in the tissue. So anything after this point is purely bremsstrahlung contamination. Bremsstrahlung contamination comes from the electron interactions within the treatment head and the scattering foil, and it is X-ray contamination. They're photons that are contaminating the beam. They're always present, except they're dwarfed by the dose of the electrons back here, and then they show up after the electrons stop depositing their dose, and you're left over with the contamination. It's roughly 0.5% for 6E, and it can vary between 3 to 5% for 20E. Okay. Again, R50 is used as an energy qualifier by the physicist. The dosimetrist, as a treatment planner, you're really not going to have to worry about it too much. It's just another beam qualifier. So, prescribing with electrons, typically, again, all situations are different, but typically prescriptions with electrons are prescribed at the 90% isodose line. And there's a reason for this. The reason is that we usually only do one electron field. So if I have a patient surface here, field is coming down, my isodose lines look like the following. This is going to look similar to talking about normalization the other time. And my tumor sits in here. This is my 100% line. These are my 90% lines. Remember, I have a build-up and fall-off 90% line. So here and here. And this is my 100. Okay, 100% goes right through the target. I can't just treat half the target. I have to normalize. You can do one of two things. You can either calculate to a lower depth, which you normally don't do with electrons, or what you can do is you prescribe to a lower isodose line, namely the 90% isodose line. And then we encompass the entire target. The same thing would be if I drew a target here on my percent depth dose curve. I can't cover it with 100%. I need to renormalize and make 90% my new 100%. Therefore encompassing the entire target in the isodose. Okay. Let's see, inverse square law. There's inverse square law for electrons. I guess we'll have to go over that in a different point in time because that'll take a little explanation. Anyway, so you got it. Look this over in Kahn, Bentel, electrons. Memorize this, and definitely memorize this for your board exams because you will need it 100%. In the last lecture we discussed introduction and basics to electron beam dosimetry, compared an electron beam to a photon beam, and then we compared low energy electron beam to a high energy electron beam, and we discussed the major particulars about those percent depth dose beams and the characteristics. And I kind of drew out this table, and this is something that you should keep in mind, as well as these are definitely points that should be memorized and kept for your board exam. So after talking about the basics, let's talk about how you calculate monitor units for electron fields. So electron fields are set up as a fixed SSD field. They are not parallel opposed. They are not wedged. You do not use MLCs. The electrons are usually set up as a single field. In rare circumstances, we will create abutting electron fields to treat curved body surfaces, but those are far and few between. The monitor unit equation is similar to photons. Where we have monitor unit is dose and centigrade on top. An output factor is the output factor for the particular cone that you're using. Most linear accelerators come with 5 or 6 cone sizes. The standard cones and a variant are 6 by 6, 10 by 10, 15 by 15, 20 by 20, and 25 by 25 centimeter cones. The next is we have a cutout factor, COF. Output factor has to do with the cone size. Cutout factor has to do with the size of your cutout that you place inside of the cone. Isodose line is your prescription or your normalization. Typically it's 90% as described by the last video. And then an inverse square law, which I believe the soft chalk lectures describe it as a gap calculation, which is used for extended SSD electron treatments. So going first with the output factor, on linear accelerators, the machines are hard-coded so that when you insert a particular electron cone into the machine, it automatically dials up a set of field sizes. Those field sizes are hard-coded because the output that you get from the electrons varies dramatically on field size. So instead of the therapist being able to dial up whatever field size they want to, the physicist only has to measure one set of output factors per cone because the jaws always go to the same spot. The cutout factor can change. You can have multiple different shaped cutouts, almost an infinite number. Most departments have a standard cutout set that they use that they put in the data book. Some facilities don't have any library, and the physicist will measure the cutout for each patient. The isodose line is typically prescribed at 90%, as described by the last lecture. Historically, they used to prescribe electron prescriptions at 80%. Now 90% is pretty much the standard, sometimes for higher energy. The physician will tweak it to 95%, although 90% is usually the standard. And the inverse square law again is a gap calculation. We need an inverse square law because as we change from 100 centimeters to 105 or 110 centimeters, the output of the machine changes as we change the distance from the calibration point. Inverse square law is interesting. I'll make a small comment on this. I won't go too much into it. Is that the inverse square law always depends on the distance from your source, your point source. But with electrons, there is no point source because in the treatment head of the machine, typically for photons, I shouldn't say typically, for photons, you have the electron beam comes down out of the bending magnet, hits the target, and then you get the shower of Bremsstrahlung X-rays below. This becomes your source, your point source for the X-rays. For electron treatments, that target is moved out of the way. Target is moved out of the way. Electron beams come out of the bending magnet. There's no target. They come straight until they hit the scattering foil, and then you get a shower of electrons that come down here. So you might say when doing an inverse square law, well, what's my SSD, my source to skin distance? Here there's a source to skin distance. Here's my source. There's no source here. There's no source here. My electron beam comes out of the accelerator through the bending magnet and then down. There's no particular source. So what we do is you kind of backwards extrapolate the quote-unquote divergence of this beam, right, backwards to a point in space that you call the source or the virtual source. So you have a virtual source to skin distance. Or and SSD effective source to skin distance. So dealing with it, dealing with the electron dose calcs, typically if you have a patient surface here and then you have a tumor, two centimeters deep, physician's going to prescribe 90 for a 10 by 10 cone. Oh, I should make a comment. Typically, departments they have a standard cone size that equals 1.0 for their output that they do their calibration for, just like photon energies. 10 by 10 is standard. Normally, 10 by 10 is standard for electrons, although it varies by institution. Some institutions do 15 by 15. A lot of times, you won't see very much change between the outputs for a 10 by 10 and a 15 by 15 cone size. In fact, I encourage you to look at your different output factors for the electrons, and you'll notice that there's not a huge difference between them, just a few percent. He's going to prescribe an energy, a cone, maybe a cutout. In this case, we'll just say open. He's going to prescribe it at a specified SSD and depth, usually Dmax. He's going to deliver 200 centigrade. So the physician's going to give you energy, SSD, cone, dose, and then a normalization. Okay. Even though the departments have percent depth dose tables with their electron data, normally physicians prescribe at Dmax, and instead of adjusting by percent depth dose, they might tweak by normalization percentage. So instead of prescribing at 90%, they want it to go a little bit deeper. We'll prescribe at 87% or 85%. The exact same thing can be done by adding a percent depth dose factor and calculating to a different depth. They both do the exact same thing. All we're doing is normalizing the dose to a deeper point in space. And by normalizing the dose to a deeper point in space, we are pumping more monitor units in to drive that dose deeper. So for this case, MU is going to be 200 centigrade. My 10 by 10 output factor is 1 centigrade per MU. My cone factor, since it's an or my cutoff factor, since it's an open field, is just going to be 1.0. I don't have any additional cutoff factor. My isodose line that I'm prescribing to is 90%. And since I'm at 100 centimeter SSD, my inverse square law factor is just 1.0. If we take 200 divided by 0.9, we end up getting 222 MU. This is fairly standard. Some places are fairly particular. If you go to, they want everything written out exactly, and maybe the output factor is 1.01. It's 1% higher. 1.02. It's not going to make a huge difference in this number. 222 for 200 centigrade is a pretty standard number at 90%. Okay. Even if you use a different cutout, and the cutout factor, let's say the cutout factor gives you 1.005. Okay, so my MU is going to be 200 divided by 1 times 1.005 times 0.9 times 1. So if I take 222 divided by 1.005, I get 221. So even though I put a cutout factor in here of 1.005, I still get 221, which is about a 0.5% different from 222. Okay, so this is the standard for monitor unit calculations for electrons. These are what the physician is going to give you. He's going to give you, he or she is going to give you energy. They're going to give you SSD, depth, which normally is going to be Dmax. Okay, they're going to give you dose prescribed at some sort of isodose line. Okay, cone size. These you should be able to do on the fly. Electron calculations are extraordinarily easy, and you should be able to go out to the machine. The physician has an emergency patient that's coming in, a fungating mass, and he calls the dosimetrist out to the machine and says, I need to deliver 500 centigrade in one shot. We're going to do 100 centimeter SSD. 9E to 90% for a 15 by 15 cone size. Okay, you should be able to whip this out without any problem at all. So there's one factor in here that I didn't put was PDD. Normally, the percent depth dose is 1.0. Okay, it's 100% we're prescribing to Dmax. If we're not prescribing to Dmax, then you need a percent depth dose factor that modifies the attenuation of the beam.